All right, and now for the final problem that was in our 3.5 notes over Newton's law of cooling. All right, before I dive into all this, because sometimes you look at this, it looks kind of hectic, let me make Newton's law of cooling very simple. If you have an object and it has a certain temperature, let's say it's a super hot object, and then you place it into a space that has a different temperature. Maybe you place it into a bowl of water, or you just place it into a room. You put it somewhere, and think about it. Over time, that hot object is going to cool. But it could only cool to as low as the temperature of where it's at. So if you take a 100-degree hot metal ball, I don't know, and you put it into a pot of water that's 40 degrees, well, that object is going to eventually cool down and cool down and cool down and cool down until it hits 4 degrees. And then at some point, over the course of so many minutes, everything in that pot will be 40 degrees. Pretty simple. Or if you take a, I don't know, again, take a hot piece of metal and you bring it into a room, and that room has a consistent temperature of 60 degrees. That hot piece of metal is going to slowly cool and cool and cool and cool. And over so many minutes, eventually that piece of metal will hit 60 degrees. It cannot become colder than 60 degrees because it's in a room that's 60 degrees. So pretty simple concept, I hope. But here is how we're actually going to put all this together. So Newton's law of cooling says an object that has been heated will cool to the temperature of the medium in which it is placed. Now, when we say medium, we mean, the where we put it. So don't overcomplicate that. So an object that has been heated will cool to the temperature of the place in which it is placed, right? Such as the surrounding air or water, as I said, either thing of water or the room. Now, the temperature T of that object at time T can be modeled by. So at any particular time, the temperature of that object can be found. So if you plug in 3 minutes, what's the temperature? Plug in 4 minutes, what's the temperature? Plug in 20 minutes, what's the temperature? And a model for the temperature based on a certain time is this. T sub m plus, in parentheses, T sub O minus T sub m equals E, or not equals, multiplied by E raised to the negative KT. All right, don't let this be confusing because it's actually not. You're going to see that in an example in a moment. This is the temperature of the median. That's T sub m. That is the temperature of where the object is going. So if you place it into a bowl of water that's 40 degrees, there's your median temperature. That's the temperature that it's going to eventually become. If you place it into a room that's 60 degrees, that's your temperature initial, not the initial, but the temperature of where you're putting the object. Hopefully that makes sense. And then T sub 0 right here, this is the initial temperature of that object. So it's really simple. Like, these numbers are all going to be given to you. You will know the temperature of the room you're going into. You will know the initial temperature of that object. And T is time. Now, the only other thing is K. Now, E is not a variable. E is a number. We know that. It's a base. K is a constant of cooling. Okay? Now, different objects have different constants of cooling. So K is going to be different based on that particular object. So we will have to do a little bit of work to find K, and I'm going to show you that in the next example. Now, I know it looks confusing. I will give you this formula on any test or quiz. Don't worry about having to memorize it, okay? You just have to understand how it works, and hopefully after I show you an example, you're going to completely understand how it works. Now, the other thing worth mentioning is this. The limit of the temperature as time goes towards infinity is the temperature of that medium. Now, think about that for a second. If you place a super hot object into a 60-degree room, that's the temperature of the medium that you're placing it into. As time goes on and on and on and on and on, as time goes on towards infinity, the temperature of that object will only ever get to 60 degrees. It cannot get cooler than the room it's placed into. So that makes sense, right? That's a limit, right? The limit of that temperature as time goes towards infinity is the temperature of the medium, the temperature of the place it was put. All right, this model assumes that the surrounding medium, although taking heat from the object, essentially maintains a constant temperature. Okay, and again, this was named after an English mathematician, Isaac Newton. Hopefully you guys all know about him. All right, so let's just show, honestly, I know it seems a little confusing, but after I show an example, you're going to realize how easy it is. The hardest part about this formula, which is what we're learning right now, is finding that K value. because everything else is just plugging in, right? T is a time. These other capital T's are values that you will be given. The hardest part, it's not really that hard, is finding K. All right, so here we go. A hard-boiled egg at a temperature of 96 degrees. Okay, so right away, the initial temperature of this egg, the initial temperature, T sub 0, is 96 degrees. It's placed into 16-degree water to cool. Okay, that's my medium temperature. It's placed into a bowl of water, and that bowl of water is 16 degrees. So again, over time, as time ticks away forever, eventually that egg is going to cool to 16 degrees and it cannot cool anymore. All right. 4 minutes later, so at the 4-minute mark, this is actually accorded, at the 4-minute mark, the temperature of the egg is 45 degrees. So again, after 4 minutes, it has started at 96 and has cooled down. It's not all the way down to the 16 degrees yet, but it is getting there. All right, it wants us to use Newton's law of cooling to determine when the temperature of the egg will be 20 degrees. Now, I cannot answer that question until I first build the model. So let's build the model. All right, the model is capital T. The temperature of that egg at a given time is, all right, I'm following the model right here. Here we go. The medium temperature, that's the temperature of where I'm putting my object. That's 16. Plus, in parentheses, I got to take my initial temperature, subtract the medium temperature. I can actually do that in my head. 96 minus 16. I'm actually going to write it so you see me using it, but that is going to be an 80. I can do that in 1 second. And then it's multiplied by e to the negative kt. I have no idea what k is. That's what I do need to find. So just kind of cleaning things up a little bit here. The temperature of the object is 16 plus 80 e to the negative kt. Now again, T is the variable, the temperature, or excuse me, the time, lowercase t, that's the time. Capital T is the temperature. I need to figure out what K is. That's where this information right here is going to come in handy. Because they did tell me that the temperature is 45 degrees when T is 4 minutes. So that's going to be negative 4K if I replace that. So I'm using this known point to help me solve for K. Therefore, I have the final model because I almost have the final model. It's almost here, but I need to know what that K value is. So I'm going to use this given information to help me solve for K. 45 is the temperature. At 4 minutes, I plugged in 4 for lowercase t. I still got to solve for K. But what have we been doing for the last couple of days? Working on solving. So I got to isolate the exponential portion. So I need to isolate this exponential part right here. So I'm going to subtract 16. 45 minus 16 is 29. Equals 80 e to the negative 4k. Divide by 80. 80 divided by 80 is 1. 1 times e to the negative 4k is e to the negative 4k. 29 divided by 80, you could grab a calculator if you want. I have one right here, 29 divided by 80. But again, it's going to be some decimal. Now that actually is a terminating decimal, so I'd be okay with 0.3625. But I'm going to leave the fraction. You know how much I love fractions. All right, now that the exponential part has been isolated to solve for the k in the variable, I am going to need a log. The base of my log is going to be an e, so a natural log. Logs always equal the exponent, so I'm going to equal the negative 4k. And inside the natural log is the 29 over 80. So natural log of 29 over 80 equals the exponent at negative 4k. All right, now, again, I could go to my calculator to figure out what the natural log of 29 divided by 80 is. Some crazy ugly decimal that I don't want to write down on my paper because I don't want to write round in the middle of a problem, but there it is. And I do need to do one more step to solve for k. I need to take that ugly decimal and divide by negative 4. And I get a final value for k to be 0.254. So 0.254 is my k value. Now, if I really want to be super accurate, I actually could store that. You can use that STO button on the bottom left. Store that as, alpha A, whatever. Just that way I have it stored completely. I'll do that just to kind of show you how it could change the answer. But, I'm okay with 3 decimals. All right, now I want to go back and actually write out my final equation. The temperature based on the time of the object sitting in this water is 16 plus 80 e to the negative 0.254 t. All I did was I substituted K in there. Don't forget the negative sign needs to be there, right? The negative is I mean, it's on the K, but K ended up being positive, but there's a negative in the formula. That K turns into a negative. All right, so there's my formula. Now I have the final formula that can tell me the temperature of this egg at any given time. So final question asked me about 20 minutes. So I'm going to plug in 20 minutes and figure out what the temperature is. So 16 plus 80 e to the negative 0.254 times 20. And of course, I'm going to grab a calculator for that. So we have 16 plus 80. And I'm going to grab my e, which is second natural log, to get the e, raised to the negative 0.254. And then times 20. So I'm literally just plugging in 20 into the equation to figure out what the temperature is. And there it is, 16.498 degrees. So it's almost down, probably not much longer, but it's almost down to that medium temperature, which was the temperature of the water that I put it in. So 16.498. 16.498 degrees. So it's almost there. Now, real quick, I do want to show you guys this real quick because I think it would be worth just to kind of look at. If I use that stored number, because remember that 0.254 was rounded, and if that's a number in a problem, you probably shouldn't round it. I just want to see what the difference is here. So I'm going to raise it to the negative, and then I'm going to grab alpha A, because remember, my calculator thinks A is the 0.2536827.012, keeping all the decimals, and then times the 20. And, well, I did something wrong. Let me go there. Sorry, that's my fault. It should be a negative sign. I used a minus. It should have been a negative. So sorry about that. So there, it's 16.501. So, I mean, I got 16.549 when I rounded. 498, excuse me, I can't read. 16.498. Using all of the decimals at 16.50. So, it is recommended that you store it. That way you don't use any rounding. But, it is a number that you need to use again. So 3 decimals isn't the end of the world. But if you're looking for a really exact answer, it'd be 16.50 degrees. So it is getting closer and closer to the temperature of the room that we cooled. So again, let me just walk through the process one more time. It's a little bit more of a complicated problem. But first, it starts off with the formula for the temperature after T minutes. Don't overcomplicate this. I will give you that formula. We're plugged in 16. That's the temperature of the medium. That's where I'm putting the object in. That's the 16 degrees. And then I have plus, and then I have to do quick math. You can even do this math separately if you want. It's the initial temperature, 96, minus the temperature that you're going into. So that's that 80 degrees there. That's where that 80 came from. And then e to the negative KT. But again, you got to figure out what K is. K, it all depends. A hard-boiled egg might have a different K than, say, a piece of metal or anything else. Whatever. Everything's going to have its own K value. So I do have that given information that at 4 minutes, we're at 45 degrees. So I could plug in 45 for the temperature, plug in 4 for T, and then I could solve for the K value. And that's where we learned all the solving recently that got me to the K value. Now I have my final model over here in black, and that final model has the K value in it. And now I could plug in 20 minutes or any time. I asked for 20, but I could ask you about 30 minutes or 15 minutes or however many minutes, and then you could get the temperature. Okay? Pretty simple. Hope it's not too bad, and hopefully that made sense.